Up until this point, everything I've shown you has involved Ks that were too close together. I haven't talked about concentrations. Let's look at this. There's 0.1 molar HCl. And there's 0.00000001 molar HCl. This is 10 to the minus 7 molar. Get rid of my spectators. And this right here is a beaker of 0.1 molar H+. Now you know it also has 10 to the minus 7 molar H+ from water. But because this number is so much larger than this number here, I've been very conveniently ignoring it and saying that H+ is equal to Ca. Well, what about down here? Here I've got a beaker, and it's got 10 to the minus 7 molar H+ from HCl, but we cannot deny the fact that there is 10 to the minus 7 molar H+ from water. Once again, I got issues, because the equation I use for HCl's calculation is that H+ is equal to Ca. That accounts for the green protons, all right, but where are my orange protons accounted for? I need to find a way to somehow incorporate a recognition of that H+ that comes from the water. I've got to find a way to put Kw into this equation. So that's the challenge I have. I have to come up with a strategy for being able to account for all the different species that are in solution. What is it that people do to make that happen? When people solve complex equilibria, they typically solve for it by setting up a series of equations in terms of the different species that are present, the different variables that are present. And there's always this general rule, there's my rule of thumb there, that says if the number of equations is equal to or greater than the number of unknowns, then I can solve. For example, here's an easy one. H+ is equal to Ka times Ca to the 1/2. Ka, I know that. Ca, I know that. H+, solve for it. So I've got this one equation here. I know everything that's here. One equation, one unknown, you can solve. But what happens when I have more than one thing that's not known? At that point, I need to develop a strategy in which I take these multiple equations and I put them together to work on them. So let's look at an example of this problem in action. What's the pH of a 0.1 molar sodium bicarbonate solution? Well, let me write down all of the different kinds of unknowns that are sitting in this solution. First of all, I know that in this beaker there's H+ and there's OH-. Those are always present in solution. I know that there's sodium ion in solution. I can see it right there. I know that there's bicarbonate in solution. But you know what? That bicarbonate, it can lose a proton, as we'll learn when we look at polyprotic acid systems. So there is a fifth unknown. And you know what? That bicarbonate can pick up a proton and make carbonic acid. So I've got 6 unknowns when I throw 0.1 molar sodium bicarbonate in solution. The ones from water, the salt and its anion, and some species formed through acid-base chemistry. If I want to know the pH of this system, or the pOH, or the PNA+, or the P bicarbonate, or the P carbonate, or the P carbonic acid, if I want to know any of those unknown concentrations, I can know them. But I have to be able to account for all 6 unknowns at the same time. I have to have 6 equations written in terms of these compounds. And if I have 6 equations in terms of those compounds, then I have determined the system. And if I can solve them simultaneously, I have my answer. So what we're confronted by then is the need to come up with equations we can use. And what I'm going to show you is that we in fact have these equations. The equations are always built on the following 3 different categories that we can work with. Kw, which provides us collections of equations. The acid-base constants that provide us with collections of equations. And finally, the mass and charge balance equations that I'll introduce in just a moment. These are the sources of the equations that I am going to be able to use to solve for an unknown. So we're going to go ahead and explore this right now. I'm going to come up with 6 equations at least that involve these 6 different unknowns, and I'm going to write them down next to each other, and boom, I'm going to solve them.